Hey guys, this is, I believe, the fourth video from PowerPoint 7.9 Intermolecular Forces. So I'm going to quickly go through. This slide is just talking about the differences between intermolecular force and intramolecular force. Intramolecular force is within a molecule, and inter is between two or more molecules. Okay, so intra is like all the bonds that we've been talking about, covalent, ionic, metallic, and then intermolecular forces is what this lesson is about. So it's between molecules, it holds particles together, and this is relatively weak. The intramolecular forces is, like I said, within molecules, holds the atoms together, and then here's some examples, and these are relatively strong. Okay, so the three intermolecular forces that you need to know are dispersion forces, dipole interactions, and hydrogen bonding. All of these forces are what determine molecules, whether they're in a solid, liquid, or a gas phase at certain temperatures. And so when things are held more strongly, they're usually solids at room temperature. A little bit less will be liquids, and then not at all, or very, very weak as gas. So the first two forces are under kind of this umbrella term, van der Waals forces. You don't really need to know that term. So dispersion forces are the weakest, dipole interactions are moderate, and then hydrogen bonding are strongest. I don't know if you can hear that, but Frozen 2 is playing in the background. Okay, so the first one is dispersion forces. These are for nonpolar molecules. So if you have a molecule that's nonpolar, automatically it has dispersion forces. And these are temporary polarities. It's like as things are moving around, it's like slightly polar and then it's not, and then it's slightly polar and then it's not. So this is a very weak force. Next, we have dipole interactions, and this is for polar molecules. Polar molecules meaning they have a positive end and they have a negative end, and these are opposites are attracted to each other, kind of like a magnet, okay? It's kind of an intermediate medium force. It's a permanent force, so it's not like sometimes it's here and sometimes it's not. And this affects things like physical properties, boiling point, melting point, things like that. So just to illustrate that point, here we have butane, which is a completely nonpolar molecule, and it has a very low boiling point of negative 0.5 degrees Celsius, whereas here we have acetone, which is a polar molecule. It's got a partially negative end right here, and it has a much higher boiling point. And that's because when you have something, a stronger force, holding all your molecules together, it doesn't want to change phases from, let's say, solid to a liquid or liquid to a gas. It wants to hold on strongly and prevent the molecules from phasing out or becoming into a gas phase or spreading apart, rather. The last one is hydrogen bonding. And this only occurs if you have a molecule that has hydrogen bonded to oxygen, nitrogen, or fluorine. Only that time. Even if you just have hydrogen, it doesn't automatically mean there's hydrogen bonding. It must be bonded to one of these three things. This is a strong dipole interaction, but it's kind of its own thing because it's the strongest one. So here we have water in a solution, and oxygen is bonded to H, so you have H bonding. And this very polar effect causes a partial negative and partial positive to be kind of attracted to each other, and it kind of becomes sticky. Okay, so then for each pair, let's predict which one's going to have the higher melting point. So in order for it to have a higher melting point, it means it's going to have a stronger intermolecular force because it's more difficult to pull them apart. So for this one, if you draw it out, you'll see that you have carbon in the middle with 3 hydrogens around it and a chlorine coming off of it. Well, I know that this is going to be a polar molecule. Even though there are hydrogens present, it is not hydrogen bonding because the H is not bonded to an O, an N, or an F. This is, however, going to be a polar molecule because the bond between carbon and chlorine is polar. This is going to be a non-polar molecule for 2 reasons. Number one, it's symmetrical, so already the end, it's non-polar. The second reason is because the bond between carbon and hydrogen is 0.4 difference of electronegativity, so therefore it's non-polar anyway. So this has dipole interactions, and this has dispersion forces. And the stronger force is dipole. So this molecule, CH3Cl, will have a higher melting point. For this one, SO2 versus H2O, you'll see that SO2 is a bent molecule and it has a lone pair on the central atom on S. That means that it is polar, okay? If you draw the correct Lewis structure, you'll see it's got a lone pair and it's polar. This, however, has hydrogen bonding because the oxygen is connected to the hydrogens. So we have hydrogen bonding, that's a stronger force, so this one will have a higher melting point, H2O. Between these two, okay, same thing. This is going to be a polar molecule because P will have a lone pair on it, so it's going to be polar, but NH3 has hydrogen bonding, so this one will have the higher melting point. Down here, this molecule is drawn exactly how it seems. So we have carbon with 3 hydrogen attached to the next carbon with 2 hydrogens coming off of it, which is attached to the oxygen, which is attached to the hydrogen. So this has hydrogen bonding. So that's going to be the highest intermolecular force. And this is going to be nonpolar because, like I said earlier, carbon and hydrogen bond is nonpolar. So overall, it's nonpolar. This has dispersion. This has hydrogen bonding. So this one will have the higher melting point. All right, so here we have SO2 again and H2O again, and we're going to draw the Lewis structures. We're going to label the geometry, identify polarity, and what is the strongest intermolecular force, or IFA. So here is SO2. We have a lone pair here. So this is a bent. This is the geometry shape. It's called bent. The dipole is going to go up towards the lone pair. So therefore it's polar because there's a dipole. And also it has dipole interactions because it's a polar molecule but does not have hydrogen bonding. For water, also bent. Also the dipoles, the overall dipoles point up towards the lone pair. You do not have to do these two right here. That's just to show you that the general trend is going up. You just need a general dipole, okay? And if you don't remember what dipole is, that's in another video, so check that out. So this molecule is polar, and its strongest intermolecular force is hydrogen bonding because hydrogen is connected to oxygen. For these two, okay, we have a trigonal planar. This is all completely spread out. So trigonal planar versus something like trigonal pyramidal. If nitrogen had a lone pair on it, then it would be trigonal pyramidal, but it's not. It doesn't, so it's trigonal planar. These have individual dipoles. These are optional to draw because what you're going to see is that overall it's nonpolar. So if it's nonpolar, you do not need to draw these individual dipoles, but if you do, make sure that you draw them all, or it will look like you have an overall dipole. This is showing that they all cancel each other out, so that's acceptable. Otherwise, I'd say just don't draw them if it's nonpolar. And so because it's nonpolar, it has dispersion forces. The next molecule is a little tricky. You're going to say, Mrs. Teagues, how did I know that chlorine was in the center? Because there's only one of them. So if there's only one thing, it has to be in the center, and it's got 2 lone pairs on the center. So this is a bent molecule. The overall dipole, again, just do the overall. This is acceptable. I would completely accept this if it's drawn appropriately, but you just need the overall. It's pointing towards the lone pair. It is polar, and it has dipole interactions. Okay, sigma and pi bonds, I kind of discussed in the last video as well. Here's what you need to know. All single bonds are sigma bonds. For pi bonds, first you have one sigma bond, okay, and then anything left over is a pi bond. So for double bonds, you have 1 sigma and 1 pi. For a triple bond, you have 1 sigma and 2 pi. That's it. If you have further questions on that, just let me know. For resonance, this just means can the pi bond be moved? It means it's delocalized. If it can, if the answer is yes, then the answer is yes, I have resonance. So another way you could say this is it has more than one equivalent structure. So for example, for NO3, the double bond could be on this O, or it could be on this O, or it could be on this O. All of these are the exact same drawing, okay? But you can put the pi bond on any of these other oxygens. So this structure has resonance. All right, so let's draw these. We're going to count how many sigma and pi. We're going to identify which one has resonance. Okay, so PO3 looks like this. There are 3 sigma bonds, and I know that because there's no double bonds present. So there are 3 sigma bonds, and no, there is no resonance because there's no pi bonds to move. For SO3, okay, we've got 3 sigma bonds. 1, 2, 3. And this other guy has to be a pi bond. So it doesn't matter which is which, but one of them's a sigma and one of them's a pi. And this double bond could go on any of these oxygens. So yes, it has resonance. You could put a double bond here or a double bond here. For O3, okay, we have 2 sigma, one here and one here. And then this other guy is a pi. So 2 sigma, 1 pi. And because this double bond could go on either oxygen, yes, it has resonance. For HNO, we have, again, 2 sigma, one here, and 1 pi. And because this hydrogen cannot accept the double bond, it does not have resonance. Okay, so this hydrogen cannot take any more electrons, so you can't move this pi bond. So it's fine the way it is. All right, so let me know if you guys have any more questions. The classwork 7.9 answers should be posted. If not, let me know. I'd be happy to go more in detail if you guys have more questions on this. And take care.